Okay, let's get started. So our next speaker is Michael Manfra from Purdue University. This is the second part of his lecture, and his title is Direct Observation of Anyonic Braiding Statistics. Please take over.
Sure, this is, yep, now it's on. Okay, great. So this is going to be a continuation of yesterday's lecture where we tried to establish the basic principles of anyons, but also what modifications to experimental systems we needed to make in order to express in real experiments in the fractional quantum Hall regime the anyonic, the contributions to anyons to real observables. So, okay. So we went through a lot of preliminary concepts yesterday, but what I want to really focus on now is once we've made these changes or innovations into our sample and device design, what can we see with them? And so, just in summary, I think what I hope to show you at least is that Fabry-Perot interferometry allows for the direct observation of anyon braiding in the fractional quantum Hall effect. And starting with the experiment where I basically stopped yesterday, where we could see the appearance of Aronoff-Bohm oscillations in the fractional regime. That was in 2019. In 2020, we were able to take modifications of our device design and heterostructure design with input from theorists to optimize the structure, to expose anyonic statistics. And here's just the data that I'll explain in more detail later that shows the discrete phase slips associated with the removal of quasi-particles from the interferometer and the associated phase slip. Okay, so one thing to keep in mind, though, it's important, and I want to emphasize for students, is that having control over the parameters and the interactions of your device is actually extremely critical to make quantitative statements about what's going on. And so over the course of several years now, we've gone through many iterations of different device sizes, interferometer sizes, and heterostructure designs, trying to optimize to expose a particular aspect of anyons. And so it's not like it's one size fits all. If I initial experiments to 1/3, then want to go to, say, 2/5 or 2/3 or to 5/2, it's not like I can do that all in a single device. I have to plan out ahead of time, knowing the relative energy scales, and then design accordingly. So the original measurements that I showed you, just showing AB oscillations, took place in a rather, by our standards, large device, where we actually see the discrete phase slips in a slightly smaller device, but also we change the density. And I'm going to show you a fair amount of results from an even smaller device where we tune this bulk edge coupling that I've been referring to in the previous lecture as an important parameter. And we'll see how that comes in as we go. But having control over the devices, it's not just what's handed to us by nature. With some degree of feedback, we can actually design in what we want. Okay? And so just to refresh your memory from yesterday, our interferometer looks something like this. If we're at the integer state at nu equals 1, we see very clean AB oscillations, these lines of constant phase having negative slope in the delta B, delta V plane. It's highly coherent. As I showed you here, the oscillations at nu equals 1 survive up to hundreds of millikelvin. And so by putting these screening wells in, making the device relatively small, we got really robust oscillations. Then we moved on and we took that same device and turned it up, the magnetic field up to 13 Tesla to look at 1/3. And here are the AB oscillations at 1/3. Now the periodicity, the change in periodicity, tells us that they're actually, we're looking at fractionally charged quasi-particles with charge of 1/3 the bare charge of the electron. So that was very nice, and we were happy that we could actually see this kind of effect. But what you don't see in this particular example are the discrete phase slips that I mentioned that would be, the direct telltale sign of a quasi-particle, an anionic quasi-particle leaving the interference chamber. And so this was like, we're happy but sad. And I remember going to a March meeting in early, I guess, 2020 with these results, and I talked to theorists Adi Stern and Bert Rosenauer, and was saying, yeah, we're just getting the AB oscillations was cool, but we weren't seeing the phase slips. And they sort of said, and went away. And within a few months, there was a paper on the archive, subsequently published, where they basically did an analysis of the energetics in the system that we had created. And there's a sharp contrast between being in the incompressible fractional quantum Hall state, where it's really incompressible and you're at fixed filling factor, and when you go out into the flanks of the quantized plateau and you transition to a compressible state. So by compressible, I mean here that it takes very little energy to add a particle for each flux quanta introduced into the system. In the incompressible region, there's a finite energy gap, and so the system does whatever it can to maintain fixed filling factor, okay? So what their analysis told us was that there's a competition between the energy costs to create quasi-particles, that's a finite energy gap to make the quasi-particles, and the electrostatic energy costs to keep new fixed. I mean, that's the defining property of the quantum Hall effect, or the fractional quantum Hall effect, is that the density and filling factor are fixed through the relationship nu equals n over b times the magnetic flux quantum. So in order to stay at fixed filling, as you change the magnetic field, the system will have to have charge to the interior of the interferometer, and that has an electrostatic cost or penalty with it. But to create a quasi-particle, staying at fixed net charge, but creating a local change in the charge density through a quasi-particle has a finite cost too. And it's these two energy scales that we're trading off. And what I was saying yesterday about having to add these screening wells nearby, what I was really trying to do is reduce this electrostatic energy, make it less like a quantum dot, where it has a finite charging energy, and more like an inert interferometer of the optical variety. But it turns out in this first experiment, we overcooked it. We suppressed the Coulomb interaction so much that based on this analysis, we had very little chance of seeing the addition or the phase slips associated with the addition or removal of quasi-particles. So their theory predicts that in the central region of the plateau, that's denoted by B0 here, there are AB oscillations with 3 phi naught periodicity. We're talking about 1/3 now. And only when you get to some critical field that deviates from the center of the plateau do you go through a transition between the incompressible and the compressible regions. And once you reach this BC, you transition in periodicity from 3 phi naught to phi naught. At that point, it becomes easy energetically to add quasi-particles, and so each flux quantum you add, you introduce a new quasi-particle or remove one depending on which side of the flank, which flank of the central plateau you're on. So the way to think about this in a sort of cartoon fashion is in the center of the plateau, my chemical potential is in a region where the density of states is extremely low. And as I go out into the flanks, only then does the chemical potential reside in an area of finite density of states, and that's when I start adding quasi-particles. Now, it's symmetric about the center of the plateau, so there's this central region in here which has the 3 phi naught AB periodicity, and then when I get up to a certain high field or a certain low field, I see this change in behavior. And what was good is they could be fairly quantitative, at least in this approximation of how wide in B field should we have fixed filling factor and 3 finite oscillations. And it's given by a couple of parameters of the system. Delta here is the energy gap, the energy gap to create quasi-particles in the fractional quantum Hall effect. Phi naught is just the flux quantum. Nu is the filling factor. E star is the effective charge. At 1/3, it's E over 3. But here's an important part. It's also scaled by this charging energy, this capacitance, basically, the capacitance between the 2D gas and those parallel plates of two-dimensional electron gas above and below that we introduced in the experiment. And you can see that, if the gap is large and these numbers here are small, the width in magnetic field can be rather large. And it turned out if you put it in for the parameters of our first experiment, you would see that the range over which you maintain this incompressibility was wider than our experiment, the region that we could experimentally access. So that was interesting for me in that it was a rather quick feedback between having an experimental result and being, having some positive aspects of it, but not understanding all of it, and talking to the theorists. And rapidly, once Adi and Bert sent us the preprints, we kind of knew what to do. So what did we do? We made the device smaller. We scaled it down. So the next experiment was with a 1 micron by 1 micron interferometer. And we also reduced the 2-deg density. We went from about 1 times 10 to the 11 to about 7 times 10 to the 10. This moves 1/3 down in magnetic field. It gives us a bigger range over which to operate, but it also, that in of itself, the change in density scales back some of these energy scales, the gap. And so by changing the size and the density, we perturbed the parameters so that we would be able to look over a broader range around 1/3. So here's the data, the initial set of data from this second experiment. And again, you see the lines of constant phase with negative slope, AB oscillations, as you would expect from our design. And just to be clear, the periodicities, both in magnetic field and gate voltage, indicate the charge is 1/3. That the spacing here, those periodicities, gives us exactly 1/3 relative to the electron charge. So that looks good, but then you see these glitches in here, and you say, well, that's noise, that's crap, whatever. They're not, they're reproducible, and they occur at the same place. So we went forward and did a bit of analysis, and you can see these lines of positive slope in the delta B, delta V plane. And if we analyze the change in phase across one of these lines, which correspond to the removal of a quasi-particle, and you can evaluate what the phase evolution is here, you can evaluate it on the other side of the transition, and then you can say how big is that phase slip. You go ahead and do that. Delta theta is divided by 2 pi, just to be clear, is always around -1/3. Now, the phase slips, we do this a bunch of times, are experimentally in this first experiment, -2 pi times 0.31 plus or minus 0.04. Remember, I told you yesterday that theory tells us that the anyonic phase that's built up in our interferometer at nu equals 1/3 is 2 pi over 3. So this was pretty good, at least for us, and constituted, I believe, the first direct observation of anyonic statistics. These phase slips are, and the jump in phase across these transitions are the anionic phase. And so this is a way in which the interferometer can actually access a quantity that is hard to probe otherwise. Okay? So what's the explanation for the discrete phase jumps? Because unless I introduce or remove a quasi-particle, I should just have normal AB oscillations. And I told you that in the center of the plateau, I'm deep in the incompressible regime, okay? And I've suppressed the charging energy enough so that it's energetically favorable for the system to add charge continuously to maintain fixed filling, rather than every time I change by a magnetic flux quantum, introduce a quasi-particle. So you might think of it as the chemical, well, it's a little bit off, but say the chemical potential is near the center of the gap. Now, in the fractional quantum Hall effect, is an idealization to say that there's no states in the gap. Reality disorder, all samples have some level of disorder in them, and there's always some density of states in the gap. It can be very small, and those states are localized, so you don't see them in bulk transport experiments, but there's always some finite density. So what happens is that along these particular lines, the energetic balance changes. By disorder, there's a local minima where it's easier to add a quasi-particle than add charge, given this balance between the electrostatic energy and the energy to create a quasi-particle. When those two are equal, or the energy to add the quasi-particle is slightly less, then we can have these discrete jumps. Now, there's only a few of them, meaning the disorder is relatively low. They're not proliferating every time we change the magnetic field, but there are certain locations in magnetic field and gate space where it's energetically favorable to add a quasi-particle. And so there are things that are constant, and there are things that are not constant in this. And so while the slope of these lines, which I'll tell you about in a second, is a quantity that we can measure and control, the spacing between them, between the jumps, is not. That's still, at this stage, dictated by the vagaries of disorder in the system, okay? But the phase jumps themselves are clustered around 1/3. So we have a way of understanding features of this data, and I'll delve into that a little bit more to try to convince you that we understand the parameters of our devices, and in fact can design in parameters that we like. So now there's these lines where the phase slips take place have a finite slope in the B delta V plane, and they have a positive slope. And as I just tried to argue, the quasi-particle enters or leaves when the electrostatic energy exceeds the quasi-particle energy. So these lines where the phase slips take place should correspond to fixed charge. We call it delta Q net. There's a lot of details about how you define the various contributions to the net charge, but the salient point is that along these lines, the charge on the device is fixed. It's not changing. So increasing B in the abstract, you think it increases the condensate charge, right? If I increase the magnetic field, the degeneracy increases, I can accommodate more particles into the ground state. So that would favor removal of any quasi-particles that may be, that aren't in the ground state condensate, while increasing VG favors adding quasi-particles. Now, the net charge on the system looks complicated, but it's really not. There's the condensate charge, there's the charge associated with the localized quasi-particles, there's the background charge, which is essentially, in these structures, they're modulation dope, so the electrons come from electrons donated from silicon atoms that leave behind a positive ion. That's the background charge. And of course, we do have gates. So we can add charge by actuating these gates. And what we need to know, though, is the lever arm, how a change in the gate potential results in a change in the net charge. So that's parameterized by this constant here called alpha bulk. That's a lever arm. And if anyone's familiar with quantum dot physics, you know, this is something that you can map out. You'd say, okay, I'm moving charge in and out of my quantum dot. I can see it, say, through Coulomb blockade spectra. And how much did I have to wiggle the gate in order to affect the change in the charge? And that's how you can figure out what the lever arm is. Now, I'll show you a little bit later, but these are things that we can measure directly in the device. This isn't like a free parameter. We can measure the lever arms, the total lever arm. That means the coupling to all charge. We can measure the lever arm to charge along the edge. That's the gapless edge modes. And we can then figure out what the alpha to the bulk is. That's inside the interferometer. And so these are measured quantities extracted from the measurement. And if we say that the charge along these lines where the facelifts must happen is fixed, it obviously means the derivative of this is 0. And you would figure out what that means from our lever arms, and the slope is about 0.44 millivolts per millitesla. If you just slap a line down here and look at what the slopes are, that is about 0.5 millivolts per millitesla. So there's very good correspondence between where these facelifts happen in the delta B, delta V plane, and considerations of the lever arms in the problem. So that's not arbitrary. Okay. Let's see. Okay, that went away. Now, that was in the narrow region in the center of the plateau. What if I start deviating? I move the magnetic field off the center of the plateau. So, you know, I go from this yellow region in the center, and then I go out into the flanks. Well, there's very dramatic change in the interference pattern. And this, in and of itself, as I'll try to show you, is indicative of the presence of anyons. If these were just electrons, the pattern of change when you go from the incompressible to the compressible region would not look the same. But let's just go through the data. So now I just take a much wider range of magnetic field and I monitor the interference. And I have this central region that I've already shown you. But then I go out, and that's about 450 millitesla wide. You go out into the flanks, and there's two dramatic effects. One is that the intensity of the oscillations is dramatically suppressed. The interference itself is, it's not lost, but it's highly suppressed. In addition, it's hard to see on the board probably, but it loses magnetic field dependence it had in here. There's still, you know, a periodicity in gate voltage, but it's lost the magnetic field dependence. And you know, at first blush, it just looks like it's going to crap, right? But as I'm going to try to show you, that in itself is an indicative of that we're dealing with anyons at the 1/3 state, and we have made a transition from an incompressible region to a compressible region. So let me show you that in a little bit more detail, and then I'll show you how we modified our device yet again to accentuate what's going on in the compressible regions, okay? So you can imagine in the central region, the chemical potentials mid-gap, not many states available. But then as I move out to the flanks, I start moving into a region where it's easier, the density of states is higher, it's easier to create quasi-particles. I deviate far enough from the center of the plateau so that the quasi-particles proliferate, you know, there's a one-to-one correspondence between quasi-particles and the insertion of the magnetic flux quanta. Of course, that happens not only on the low field side, it happens on the high field side where the red circles here are indicative of quasi-holes, or if you want, the removal of quasi-particles. Okay, so this is the picture we have. And, you know, these are just cartoons. This is real data, but these are cartoons. But how does this really comport with theoretical expectations? Okay, well, this looks a little crowded. We determined that the central incompressible region is about 450 millitesla, and I'm going to show you through measurements and then comparison to the theory of Stern and Rosenauer, that makes sense. So, but let's think about what happens. There's a prediction for a transition from 3 phi naught period AB oscillations to a phi naught period due to quasi-particles in the low field or region, or quasi-holes in the high field, okay? And the interference phase, the thing that's being measured here, follows this form that I showed you yesterday. But remember, AB evolution is continuous. I change the magnetic field and the phase evolves. So we change the flux phi naught, then the change in due to AB evolution is 2 pi over 3. But every time an anion is added, or in this case on the high field side, removed, that's discrete. The change because of the statistical phase contribution is discrete, and that's minus 2 pi over 3. So on average, there's 0 change in phase as I evolve the magnetic field. This is what gives you the flatness, why we lost the magnetic field dependence. When I start generating lots of quasi-particles, my AB evolution in magnetic field is compensated each time a quasi-particle is removed by an exact loss of the same amount of phase. So the anionic contribution is discrete, but the quasi-particle number in this regime is likely smeared. And the reason that is because I quenched the charge draining so much. I mean, I just want, I want to get rid of all the quantum dot physics, that I made that energy scale way too small relative to KT in my experiments. The temperature scale that you would predict for the parameters of our experiment was 2 millikelvin. And there's no experiment with electrons in gallium arsenide that are at 2 millikelvin. So what's actually happening here is that the quasi-particle number is probably fluctuating on the time scale of the circulating current and around the edge, and that's why we don't see this constant evolution and discrete facelifts. It just looks like there's no magnetic field dependence. So smearing occurs when the density is high due to the screening wells we put in, but the energy scale is really small. And so that's why we see, it also explains the loss of coherence in that the suppression of the amplitude overall, of course, is suppressed thermally by the random excitation of quasi-particles, okay? So you may think I'm putting a lot of faith in that data that I have. I'll back it up with more data to show you why that interpretation makes sense. If you do a simple simulation of interference at 1/3, now we're doing basically thermal averaging, what you might expect is in the 0 temperature limit, you have these nice lines of constant phase and negative slope. And then as you transition out into the compressible regions, you see this sawtooth pattern. But as you raise the temperature, the electrostatic energy is given by the expression below. As you start raising the temperature, what you start to see is a smearing out of those sawtooth behavior. So by, when you get to a region that is experimentally accessible in that experiment I just told you, the lines are flattened out and smeared. Okay, so when thermal smearing of the quasi-particle numbers included, simulations qualitatively match the experiment, flat lines of constant conductance. Okay, so let's get into a little bit more detail and see if the numbers actually match in the way I suggested. So again, we measure the incompressible region to be about 450 millitesla. There's this formula for Rosenau and Stern. I measure the activation energy, the gap for this particular case. In the bulk gap is about 5.5 Kelvin. That goes into the here. I know nu, I know the effective charge. I know the capacitance from the Coulomb blockade diamonds. That gives me an expected region via theory about 530 millitesla. So the correspondence isn't so bad there. So remember the picture here is that as we change the flux by phi naught, the AB evolution is continuous, and that's positive 2 pi over 3. When I get to a phi naught insertion and I remove a quasi-particle, there's a discontinuous change in the statistical angle of minus 2 pi over 3. So on average, 0 change. So while the anyonic phase, the contribution from the anyonic phase is discrete, the quasi-particle is thermally smeared. The temperature scale is quite small. I don't know, it's 2 or 4 millikelvin, doesn't matter. Smaller than KT, okay? Now, does this bear, oh, well, what we did is we looked at the coherency in the incompressible region by looking at the decay and amplitude of interference as a function of temperature. And so the temperature, and this is a log linear plot here. So what you see, these are the data points we're measuring at various temperatures of the AB oscillations in that incompressible region. And there's an effective energy scale that can be extracted from this log linear plot of about 100 millikelvin. Now I do the same experiment, but I go out into the flanks, both on the high field and the low field side. And you see that there's a much more precipitous drop in the interference amplitude with temperature. In the incompressible regions, the temperature scale is roughly a third, a little less than a third, about 30 millikelvin. So this, 3 times change in the energy scale is quite dramatic, and it suggests that the high density of states leads to dephasing due to thermal smearing of the quasi-particle number. Now, if there were no statistical angle, that quasi-particle number was, number of electrons was fluctuating, the interference, if they were just in electrons, wouldn't care. It's the fact that they're anyons, and the overall interference phase depends on the number of localized quasi-particles that gives you this decoherence. So you could argue that the incompressibility protects the interference from dephasing. That's up here. And we have more dephasing in the compressible regions. So actually, there was theory that predated our work, experimental work. We only figured it out after the fact of this concept of topological dephasing by Park, Geffen, and Sim. Okay? So this quantity, the NL that goes into the interference phase here is thermally smeared. And so here we're deep in the gap, and when we're in the flanks, we're in the compressible regions, and it's easier to thermally smear. So for fun, we like to say sometimes this is the first experimental evidence of topological protection against dephasing. Or if you're, the half-filled glass kind of person, then it's the first example of topological dephasing, because the fact that these are topological objects and the interference phase critically depends on the number of localized quasi-particles is what enhances the dephasing in the flanks, okay? But nevertheless, that behavior is indicative of the presence of anyons. So even though you might see it as a loss of intensity and all this other stuff, if they weren't anyons, you get quite different behavior, okay? So then we have this result. Okay, great, we can see the anyonic phase slips, we get the right value for 1/3, and there's interesting things happening in the compressible regions due to the presence of anyons. But what can we do to further solidify this interpretation and at least convince ourselves that we have control over our devices and that these models that we've constructed or the theorists have constructed for us actually work? So what we did is we went down in density again and we made the device even smaller. This enhances this charging energy, not so much that we can't see the anyons, but it makes the energy scales larger so some of the features may be clear. So I'm going to get to this now, but here's the interference over in a device that's now 800 nanometers by 800 nanometers, and the density has been dropped to 6 times 10 to the 10. Okay, so there's very clear discrete phase slips. But now look at the transition between the incompressible region to the compressible region. And I've zoomed in here. These are very clearly the phase slips, but the transition is clear. And now you see modulations. This is the real data. And now we can actually see the discreteness of the anyonic phase slips and balancing the continuous evolution of AB. Okay, so I'll get into this now. We went to a small interferometer, cut down the size, we reduced the density some more, and here's the overall picture. We have a phase evolution in here with some discrete jumps with a particular periodicity. The periodicity is much smaller in the flanks. That's consistent with the 3 phi naught to phi naught change. And in the compressible regions, you can now see that the intensity is higher, first of all. It doesn't look just like noise. And you can see the discrete interaction between AB evolution and removal of a quasi-particle, the continuous AB evolution and the discreteness of removing quasi-particles. Okay, so they're extremely sharp phase slips and clear transitions to the compressible regime. If we look at the temperature dependence of this, this is down at base, 10 millikelvin, and all we do is try to repeat it, but we elevate the temperature to 50 millikelvin and 90 millikelvin. You see an evolution where everything gets rounded and softened. And by the time we're at 90 or 100 millikelvin, this data looks very much like the data I showed you originally in the device that we first measured, anyonic braiding, where it kind of just looks all washed out in the compressible regions and low intensity. Here, we've changed the energy scales by the material and device parameters, but we've gone back to the old regime by increasing temperature. This makes the connection, or at least for me it does, in that we can see what we saw in the other device, but now just at elevated temperatures. So the modulations decay quickly with temperature, leaving smooth lines of constant phase with almost no magnetic field dependence. And even in the incompressible region, everything gets rounded over and less sharp. And that's just what you'd expect. So sometimes I get asked about how reproducible is this, or how stable is it? So for fun here are 3 consecutive scans. This is all at base temperature, 10 millikelvin, where we collect the data and go up once, and then collect data on the way back down, and then collect it a third time. And the point I'd like to make is this is remarkably reproducible. To collect this data, you have to scan both B and gate voltage, and you have to collect, and you're using very small signals, so you have integration time. So each scan is about 2 hours to collect the data that goes into a plot like this. And over the course of 8 hours or something, it looks rock steady. Now, what you can also see, though, I want to point out, you see this discrete, straight, vertical line here? That is a charge fluctuation. So, the device is a mesoscopic semiconductor device, and if there's change in the, say, the dopant layer, whether a silicon atom is charged or not, that will affect the electrostatics. And so, over the course of this 8 hours, we saw 1 charge jump here. But note that this is very distinct from the anyonic phase slips. It's vertical, it has no magnetic field dependence, and it's just like a glitch, right? So it's very easy to distinguish between the anyonic phase slips and the very occasional glitch from charge noise. But we do see it, and it's recorded in the data. Okay? Now, that sounds good. I just made the device smaller, and I increased the charging energy, and everything became sharper. I saw these anyonic phase slips in the incompressible region, very sharp and precise. And then I saw the evolution in the compressible region. That's also consistent with the presence of anyons. But is there a price to be paid, or do I you know, is there any kind of trade-off? And remember, in the first experiment, I was able to show that the interference phase that we measure is equal to the anyonic phase, this minus 2 pi over 3. And the reason that they were so close to each other is because we had squashed this charging energy so much. We had made the bulk edge interaction so weak that the interference phase and the anyonic phase were essentially the same thing. The measurement gave what theory told us. In this structure, we're going to see something different when we do the quantitative analysis of the phase length. And just recall from yesterday, this is just for the integer effect, but it's the same message. If I am deep in the AB regime, we have lines of constant phase with negative slope, but there's a whole range of behavior I can expect depending on the couplings. As I mentioned, this regime of operation depends on the ratio of KIL to KI. KIL is the energy of the bulk edge coupling. How much, if I change the charge in the middle of the device, how much does the compressible edge move or care? And Ki is the edge stiffness. How much energy is the cost to change the area of the edge? And as I was discussing yesterday, depending on this ratio, you can see a whole range of behaviors. And we don't want to be at this far end of Coulomb dominated because there the statistical phase is unobservable. Many theorists contributed to this analysis, and I've listed some of the references down here. But in order to quantitatively analyze what we see in our interference experiments, the interference phase is what we measure. To relate that to the anyonic phase takes knowledge of these physical parameters, okay? So as I said, there's coupling constants. There's the edge stiffness here, Ki, and KIL, the interaction between the localized quasiparticles and the edges. This electrostatic coupling is important for the operation of the interferometer. And I think someone asked yesterday, and this is what I was alluding to, that we can write down a model of what the energy, electrostatic energy of the system is. And of course, there's a term related to Ki for the edge stiffness, and there is a cross term, which is the bulk edge coupling. Normally, in the dilute limit, we don't have to worry about the quasi-particle interaction. So, but we do need to know the edge stiffness and KIL, the bulk edge coupling, if we're going to make quantitative comparisons. Because what happens? That simple formula I gave you for the interference phase before gets modified in the presence of finite couplings. Now this looks kind of ugly, but it's really not. Here's the original term, the scaled AB oscillation evolution. Here's the term related to the anyonic phase and the number of localized quasiparticles. It's just modified by this intermediate term, which depends on a couple of things. The ratio of KIL to KI, the effective charge, and delta nu. Delta nu is the difference in filling factor if you have multiple edge states. Say you're at nu equals 2/5, and you have multiple edge states, it's for the region that's in between the two edges. Okay, at 1/3, we only have a single mode, and so it goes from 1/3 to 0. But, you know, you can look at this and see how these couplings will modify what you measure relative to the pure anyonic phase factor. They are 1/3 in the first experiment, within experimental limits. I mean, well, you know, we have error bars. What I'm going to show you now is they are not exactly 1/3 in the case where we have stronger bulk edge coupling. But as long as we measure the coupling parameters, we can work back. Okay, so let me just show you that, okay? Yeah, that's the normal experimental error on the system. As far as we can tell, the bulk edge coupling in that first experiment is suppressed sufficiently that the measurmental uncertainty gives us the theoretical value, you know, assuming that we accept that there's, you know, fluctuations due to our ability to measure it. Here, I'm going to show you a case where it demonstrably deviates from the 1/3 value, and we think we know why because of these couplings. Okay, so how do we parameterize our device so that we convince the world and ourselves that we know what we're doing? Well, there's a number of ways of looking at it. So here's the data from nu equals 1, not 1/3, where we see AB oscillations, but we still see a difference between the compressible regions and the central incompressible region by a change in the periodicity. You can actually extract the ratio KIL to KI by looking at the ratio of these periods. The fact that they're not the same in the compressible, this is, phi naught out here. And the fact that in the incompressible region, even though we just have bare electrons, there's nothing fancy going on, the AB periodicity is changed is an aspect or manifestation of the bulk edge coupling. And if you actually go through the analysis, you can see that this periodicity in the incompressible region is phi naught modified by this factor 1 minus KIL over KI in the inverse power. And we can just do the Fourier analysis. You can see that midfield, there's a clear periodicity here, and in the two flanks, we get a different one. That measurement tells us that the ratio of KIL to KI is 0.25, a moderate amount of bulk edge coupling. Okay, so that's one test. Now that only gives us the ratio. We can be more precise and actually ask what the individual contributions are. And we can do that by a host of other measurements. As I said, we can do Coulomb blockade spectroscopy at B equals 0. And then there's no distinction between the edge and the bulk. The charge in the dot is the charge in the dot. And we can figure out how, okay, gotcha, energy it takes to add and remove charge. So we get a charging energy from that. I also mentioned yesterday that looking at differential conductance measurements, we can figure out what the edge mode velocity is. Now these are more complicated measurements where we're measuring at AC but applying a finite DC bias. But from that, we can extract the edge velocity. And you can write down an expression for what the energy is. Okay, so you can see that you can estimate the internal energy from the B equals 0 Coulomb diamonds and the single particle term here from the finite bias edge state velocity measurement. That's basically telling us how much it costs to add charge to the incompressible edge. And here, by doing independent measurements, we get each quantity and we extract KIL over KI to be about 0.31. Completely independent, different measurement, same ballpark. We can do, oh, I should skip this one. Let me move on. We can do similar measurements at 1/3, where we measure differential conductance and look at the node spacing to extract out what the edge stiffness is. We can do it both in differential conductance and then actual DC measurement where we're just applying a real DC current to the system. And looking at these nodes tells us that spacing tells us about the edge velocity. And so we can extract KI, the edge stiffness, to be, in this case, 269 micro EV. And this ratio, again, extracted from the experiment, is about 0.27. So these other measurements that aren't related to the anionic phase extraction tell us what the parameters should be, okay? So then if we go back to our interference data and we look at the measured interference phase, what we see is it's not exactly 1/3. You'll see 0.22, there's one that's high, there's a couple that have 3, but what we find out is that the average phase measured, this is the interference phase, is minus 0.24, plus or minus 0.04. With it, given our measurement error bars, that is a deviation from the 1/3 that's expected. But we know the anionic phase is related to the measured interference phase through a scaling with the effective parameters. And these effective parameters I just told you were measured independently. And if we take that into account and correct for it, we come back to theta anion on average for all these is 0.32 plus minus 0.05. So what's real, at the time I thought this was the best thing ever, because as an experimentalist, it meant that we really had some understanding of the mechanisms at play in our device. It's not a new result in terms, the anionic phase at 1/3 is still 2 pi over 3, and so that's, that's a big physics result, but as an experimentalist, to say, I actually in situ can tell you how the device couplings are impacting a measurement, I thought was quite powerful. And so we've extracted the values from 2 different approaches, looking at the ratio of periods and differential conductance measurements. And the price we paid for getting these very sharp transitions is that the interference phase deviates from the anionic phase, but if you do things properly, you would get the right anionic phase, okay? In the last few minutes, the question is, so I hope I'm convincing you that, at least in this system, the combination of the theoretical models and our control of devices is sufficient that we can, go beyond just the first discovery thing of saying, oh yeah, there's anions. We can actually design things in. Now, the question everyone asks is, okay, you did it for 1/3. Can you extend it to other fractions? And it's not as easy as you might think, and I'll try to tell you why. There's been theoretical analysis of the robustness of the effects, and nu equals 1 and 1/3, the single edge mode states are deemed to be quite robust. But when you move to more complex fractions, things get more complicated. Try just making the change from 1/3 to 2/5. Well, a lot of things happen. The predicted charge is supposed to be 1/5 of the bare charge, and the statistical angle is now minus 4 pi over 5. Can we measure this? It turns out in the end, yes, but it's hard. And the reasons are myriad. There's a smaller bulk gap. Most importantly, there's multiple edge modes. Interactions may be important. The small effective charge. This delta nu that I talked about, which was 1/3 in the previous experiment, is now 1/15 because we have 2 edge modes. You must be able to independently interfere inner and outer modes. And slow AB evolution is contrasted with large discrete phase jumps. This is just a statement that says it's not a priori obvious that once you do it at 1/3, you can do it for every fraction. You have to really design your experiments to be targeting specific piece of physics, okay? And, I'm gonna run out of time, but just to give you the answer already, late last year, we were able to publish, and at nu equals 2/5, we were able to measure the charge of 1/5 and the statistical angle of minus 4 pi over 5. And remember, I told you yesterday that the interferometers allow you to measure the effective charge, the fractional statistics, and even some Luttinger liquid parameters from the edge states. So the measurement yielded E star of 0.17 plus minus 0.2. The theory told us it's 0.2. The effective anionic phase we measured was very close to minus 4 pi over 5. So how that happened, I won't have time to go into all the details, but just to give you a sense, here is in another device, we're measuring RD, which is the resistance through the device when it's biased so that you've defined the interference chamber. And RD, here's one, and the black curve here is the bulk RXY. So if you, on the same mesa. So if you just look at the bulk, it's 1/3, 2/5, 3/5, it goes ad infinitum. But if you look at RD, the transport through the device, while there's a broad range over which is fully quantized, fully transmitting at 1/3, the region over which the device is fully transmitting is much smaller than the range in which we see full quantization in the bulk. So this gives you an indication of how we shrunk down the scales. These are the individual QPC curves. We started out at full transmission of 2 modes at 2/5. We partially backscatter the inner mode. Eventually, we fully backscatter the inner mode, and there's a 1/3 quantized plateau. And then we're just scattering the outer modes. And so you have to know where you are and be able to individually interfere the inner and outer modes. I won't have time to go through this. This is the interference of the outer mode. It looks like 1/3 as it should. But if we jump ahead and look at the inner mode, it looks quite different. Okay, so it has more of this checkerboard pattern. If I had another half hour, I could tell you why it should look like this. It actually should. And the same techniques that we use to measure the couplings at 1/3, we apply to 2/5. It's a little bit harder. The math is a little bit more complicated, but the periodicities actually work out. And so what you can see is we can make a transition from a very narrow incompressible region. The region of incompressibility is quite narrow. Because of the smallness of the gaps and the size, we transition into the compressible regions much quicker. And the other thing that happens there is we lose interference almost completely. But if we go along these lines in the plane here, you see the nice, along those diagonal cuts, the nice periodicity. We can extract the phase angle. We can extract the couplings, just like we did before, to get what KIL over KI is. And using the finite bias measurements, it's about 0.2. And we were able to extract the effective anyonic phase, and it's remarkably close to -4 pi over 5. The important thing is to note here is that this effective parameter, 0.2, is not large. It's very modest finite bulk edge coupling. But it's much more impactful at 2/5 than it is at 1/3. The same amount of bulk edge coupling would be barely perceptible at 1/3, but because of the sort of tyranny of 1/nu and the smallness of the charge, it has a much more dramatic impact at 2/5. Nevertheless, if things work out and you can measure, you can actually work at 2/5 and get the right answer. So what's the summary? At 1/3, I think we have very strong evidence that we've measured anyonic statistics and found not only the phase angle itself, but its impact on interferometer performance. The same can be said now at 2/5, which is a non-trivial extension, at least for me. The lesson is that the heterostructure design, as well as the device design, is critical to the observation. And I hope I can convince you that the microscopic device parameters can be measured in situ and the impact on anyons quantified. What's next? We're working at 2/3, which has potentially counterpropagating mode, quasi-particle tunneling at 1/3, and of course, we're trying to build devices that work at 5/2 as well. Thank you.
Thank you for the great talk. Is there any questions for Michael?
So there are ideas how to generalize this to non-abelian.
There are. And so the dominant effect is the presence of the distinction between abelian and non-abelian is depending on the parity of the shared Majorana mode, you'll either see interference or not. So there's an on-off effect that should be prevalent at 5/2. So in principle, there could be even more dramatic effects than just the phase slips you see with the abelian contribution. You could have loss of interference altogether, depending on the parity of the Majorana. And that's a distinct prediction. Now, of course, that may all be smeared out too because of the same thermal effects and the energy scales being small. But there are concrete predictions of what you would see at 5/2. So there at least will be something we can compare it to.
Maybe a follow-up question on the 5/2. So if I remember correctly, there is also a neutral edge mode for 5/2.
Absolutely.
And from what you taught us, it's very important to consider the
Yeah.
And in this case, how should one think about the bulk and the neutral edge mode coupling?
Well, it's a problem. I don't, you know, we haven't done the experiment yet, so I don't know how impactful it's going to be. But you have a variety of edge structures depending on the topology that's active at 5 halves, right? And you do have neutral mode, you have counter-propagating modes, and they're neutral. Whether they contribute, I think the biggest concern is that how the interaction, not necessarily of the bulk in the edge, but the edge-edge interaction, and does it contribute to dephasing, is something that worries me a little bit more. And do I have the mutual interactions of does it renormalize, and so that the charge mode, they become mixed modes, and then we'll be dead in the water. So I can only say, the only thing that we're trying to maintain is the very sharp edge confinement potential, so that we can counteract the proclivity to reconstruct the edges. So I don't know the answer yet, but that is clearly distinct from 1/3 and 2/5. 2/5, the complication was just we had multiple modes. At 5 halves, you have neutral modes, and depending on the topological order or which way they're going, changes.
We have time for one last quick question.
In a lot of your data, like a really sharp transition from the incompressible to the compressible in like the high field side, it's much more gradual on the other.
We don't understand on the low side. It's an observation that's absolutely correct, and we still haven't figured out why. We don't know. It is true that it's cleaner on the high field side than it is on the low field side. It looks softer on the low field side, and we don't have an explanation for it yet. But it's absolutely a fact. You're right.
All right, let's thank our speaker again.
Thank you.